So if we have a bundle, so let F be a C bundle on with the model fiber F on a manifold M, and then we have this canonical projection mapping from the total space to the base. Then the projection map I, which is defined on the total space, mapping to the manifold M, which maps each fiber over X to the point X. So this is then a smooth map, right? So this now makes sense because we have turned E into a manifold. So this is a smooth map. It's not just a smooth map, it's a smooth submersion. And submersion means that the differential is onto, is always surjective. And similarly, we have other canonical maps for such a bundle, namely we have the inclusion maps of the fibers. So let's fix a point in the manifold, fix X and M, and then we also have the inclusion map. We call it iota X from the fiber on the point X into the total space. So the total space is the disjoint union of all these f-x's. So in particular we have the inclusion map of one of them, and this inclusion map is also smooth. Remember, fx was by definition a manifold, and M was by definition a manifold, and the manifold structure on E we just constructed last time. So, but now we can talk about smoothness of this map too. So this is a smooth embedding. So let's briefly check why this is the case. Proof. And smoothness of a map can be checked in local coordinates, so let's do that. And we use the coordinates that we constructed last time in order to construct the differentiable structure on the total space. And so remember how this works. So if I started with local coordinates on the manifold M and on the model fiber F, and with a local trivialization of the bundle. And from this I constructed coordinates on the total space E. Local coordinates on the total space E. So, if Y is a chart on M, Z a chart on model fiber F, and phi bullet local trivialization of the bundle, then we constructed coordinates for the total space, which were given by the y's and the z's, the y's of the foot point and the z's of the point on F that I obtain when I map the fibers to the model fiber using the local trivialization. So then y1 up to yn, z1 up to zm are coordinates, local coordinates on the total space as constructed last time. And now let's see how these maps look in these coordinate systems. So how does the map pi look? Pi is now locally given as, Well, it takes a point of the total space, so given by these coordinates y1 up to zm. And what is the result? So what's the local expression for this projection now? And you also see that the differential is surjective. So this shows I is a smooth submersion. And so concerning the embedding iota x, so iota x is locally given as, well, we can use the coordinates z1 up to zn as coordinates on the fiber when we identify the fiber fx with the model fiber using the local utilization. And if you do that, then the map is given as take a point on the fiber and insert it into the total space, exactly these coordinates. And the foot point is given by y coordinates, but that's fixed, so we have to insert the y coordinates of this special point x. So these are just some given numbers. So that's the map. And so clearly this is a smooth map, and the differential is injective. So this shows that iota x is a smooth immersion Immersion means that the differential is injective. But there's a bit more here, so I'm claiming it's an embedding rather than an immersion only. And an embedding means that the image is actually an embedded submanifold. And so the image of this inclusion is, of course, the fiber fx. So why is fx an embedded submanifold? Well, fx is locally described by the equations. Well, so as a subset of the total space, which is described by coordinates y1 to yn, z1 to zm, and it's described by the equations that these numbers are unspecified and these are given by the point x. y1 equals y1 of x all the way up to yn equals yn of x by the system of equations. And so so that means that this is a submanifold chart for the fiber fx. So therefore, fx is an embedded submanifold of the total space. Okay, so we see that this differential structure on is reasonable. So with respect to the differential structure that we have constructed, our projection map is a submersion, smooth, and the embeddings of fibers are embeddings, also smooth. Good, that's one thing. And the other thing that I want to note is how this differential structure on the total space behaves with respect to pullbacks of bundles. So let's look at the pullback of a bundle. So for this we need a map, a smooth map from some other manifold n into m. So let this be a smooth map. And then we can pull back the bundle over m to the manifold n. And this then also has a total space with a differential structure. And now, let's see. So, if I look at the total space of the pullback bundle, then I get a map from the total space over n to the total space over n as follows. So, we get an induced map, let me call it F2. tilde, which is defined on the total space of the pullback bundle to the total space of the original bundle. And how is it defined? It maps, so mapping a fiber of this bundle, so that would be F star, F, so this pullback bundle. If I insert a point of the manifold N, then we call this point U. And so this should be mapped to the total space of the original bundle over my manifold M. So I have, the foot point has to be some point of M, and what we take is the image point of U. But now if we recall the definition of pullback, then we remember that the fiber over U of the pullback bundle was defined as the fiber of the original bundle over the image point. So it's exactly this fiber, right? So, and here, so we can just take the identity map here. So this is a canonical map. And so in particular, following diagram attributes. So here we have the manifold N, here we have the manifold M, here we have the map F, here we have the projection of our bundle for our bundle F, and here the total space of that bundle. Similarly, here we have the pullback bundle and the corresponding projection here. And now we have constructed a map on the total spaces. And in fact, this diagram commutes, because a fiber over U is mapped to the fiber over F of U. So that means fiber being in the fiber of U means I go down here, then I'm over U, and then I'm mapped to F of U. And this map F tilde that I've constructed takes that fiber to fiber over F of U, which gets mapped to F of U. So obviously, by construction, this is a commutative map diagram. And now the claim is position. Both these total spaces, total spaces missing here. Both these total spaces are smooth manifolds, and the claim is that this map F tilde is also a smooth map. And in order to see this, we again look at local coordinates and well, proof. So local coordinates on this total space have been induced by coordinates on M, coordinates on the model fiber, and the lobing trivialization. The model fiber for both these bundles is the same. So we can use the same local coordinate system for the model fiber F for both of these bundles. And but these two manifolds are very different, and so we use the coordinates for this one, say y1 up to yn, and some other coordinates u1 up to uk for this manifold. And then we have to see, here we have a local trivialization, and in fact a local trivialization on this bundle induces a local trivialization for that bundle. So let's start with this observation. So let phi be a local trivialization of F, and well, now this induces local trivialization is defined on an open subset U in M. And this induces a local trivialization, which we should just call the pullback trivialization of pullback bundle on the pre-image of U, which is an open subset of N, simply by putting F star phi over a point u to be phi of f of u. Why? Because what does this thing do? This maps the fiber over f of u isomorphically to the model fiber, but this is the same thing as the fiber of the pullback bundle over u. And so we have something that maps this model fiber onto this fiber onto the model fiber. So we can also pull back the local trivializations. Now let Z be local coordinates for the model fiber, so Z1 up to Zn. And y1 up to yn local coordinates on the manifold M as before, and in addition now I have local coordinates on n, u1 up to uk, let's say the dimension of n is k, so this should be local coordinates on n. And then we get induced coordinates on both total spaces. Z, y, and phi induce coordinates on the total space of f, and z, u, and the pullback trivialization induce coordinates on the total space of the pullback bundle. And now let's see how this map f tilde looks like in these two coordinate systems. So in the induced local coordinates on the total space of F and of the pullback bundle F star F, respectively, the map F tilde takes the following form. So let's see. So we have something starting on the total space of the pullback bundle. So this has the local coordinates u1 up to uk and z1 up to zn. And so the coordinates for the manifold n and for the model fiber. And now let's do what the map F tilde does to it. To the corresponding point. So that encodes a point on the manifold n. And where is this point mapped to? Well, this diagram commutes. So this point n is mapped to the corresponding image point under F. So what we have here is basically we have to take this. We have, let me say, F. U1, UK, and then we get a point in M, and we express these in the coordinates on N. And what happens to these coordinates? Okay, so these coordinates are actually coordinates of the model fiber, but we have used the trivialization, the pullback trivialization, to identify this with the fiber at which we are looking. But this pullback trivialization over U is the same as the corresponding isomorphism over the image point. And so what we do is we take this point in the model fiber given by the coordinates Z1 up to Zn, identify this with a point in the fiber of the pullback bundle over U, which is the same as the fiber over of the original bundle over F of U, where we take the corresponding trivialization to again identify with F. But the local trivializations were the same. And so it's actually the identity map on this one, on this part. And since F is a smooth map, we see that this is a smooth map. All right, good. So that is also nice. So we always have this commutative diagram for pullback bundles, where the total space of the pullback bundle gets mapped smoothly onto the total space of the original bundle, mapping the corresponding fibers via identity. Questions about this? Yeah? Yeah, that they are C infinity compatible, that's what you mean? Yeah. We have to check this, that these, but I think we did this, I'm not quite sure, I think we did it, because if you look at the transition functions for these, so you take two such trivializations, you pull them both back, and you look at the transition functions, it turns out they are just given the original transition function composed with F. And so that's why you have a composition of two smooth things, which is again smooth. I think we discussed this last time, but I'm not sure. Yeah, but this needs to be checked, that's true. Any further questions? Okay, good. So now we know what bundles are. And also this looking at this total space and turn it into manifold, this bridges the gap to the usual definitions in the literature. And the next thing we want to do is we want to talk about connections, because we will need connections and their curvatures in order to construct characteristic forms and classes. Also, connections are needed in order to differentiate sections of bundles. So, fourth section in the chapter on preliminaries is on connections. That's what we want to discuss today. And, well, so let me start with one thing. So we start with, suppose we have a bundle. So let bullet be a C bundle on M with model fiber F. And C is a C infinity suitable category as usually. And then we can look at the following vector bundle, namely, we associated that's a bundle where the base manifold is now the total space of this bundle. So let E be total space of the bundle. And now what I'm doing to each point in E, I'm associating the following thing. So each point of the total space is sitting in precisely one fiber of the bundle. And it's the fiber F with the foot point P, pi of E. And this is a submanifold of the total space. And so we can look at its tangent space. Then this is a subvector space of the tangent space of the whole total space. So that's a subvector space of the tangent space of E. Subvector space. So what this defines me is a pre-bundle, right? So to each point I associate a certain vector space. And this is called the vertical bundle. So denote this from now on as V for vertical at the point E of my bundle F. So that's the vertical bundle. Note that F need not be a vector bundle, right? F can be anything, can be a fiber bundle, whatever. However, what we get here is a vector bundle because this is a vector space. Okay, and one way to characterize this subspace is the following claim. This vertical subspace of my bundle is the same thing as take the projection map. So the projection map maps E to the base manifold M. Take its differential at the point E, then this maps the tangent space Fe onto the tangent space of the base manifold, the point pi P. And I claim it's the kernel of this linear map. That's the same thing. And why is that? Well, let's see. If we have something in here, so I first check this inclusion. So I take a vector in here, so let x be here. So then this is a tangent vector which is tangential to the fiber, so that means it can be represented by a smooth curve in the fiber. Right, so then there exists a smooth curve C, defined at some interval, going into the fiber over the base point of E, such that C dot 0 is equal to x. Now the vector is tangential to the fiber, so it can be represented by a curve in the fiber. And if I now look at what I get here, so if I apply this to x, then this means I apply it to C dot of 0, and so by the chain rule, that's the same thing as C composed pi composed with C of t, t equals 0. But now, since this curve is entirely in the fiber, so this is always the same value. So this is always the same, independently of t. This is the same as pi of e. It doesn't change because the curve lies in one fiber. And so we have a constant curve which gets differentiated, so this gives us 0. So this tells us that x is indeed the kernel of the differential of the projection. And conversely, for the opposite inclusion, we can now show using a dimensional argument. So if I show that these two spaces have the same dimension and one is contained in the other, then they must be equal. And well, what is the dimension of the kernel of the differential of pi e? We know that this is a submersion, so the differential of this d pi, this is surjective. So that means the rank of this linear map is given by the dimension of the target space. So what is this dimension of the target space? Well, the target space is what's the target space? Where does this linear map land? The tangent space of M, exactly. So that's so the rank of this map is the dimension of M, exactly. And I want to have the dimension of the kernel. So by the dimension formula, I have to take the dimension of the domain space, which is the tangent space of E. And what's the dimension of E? Yeah, what is n? What is n? Okay, and so if I subtract the dimension of m, what do I get? So that's the dimension of the model fiber. Okay, and what's the dimension of this space? remember this was defined to be the tension space of the fiber at a point. So this is the same as the dimension of the model fiber, right? So these two spaces have the same dimension, one is contained in the other, so they must be equal. Good. Okay. So that's the vertical the vertical pre-bundle, if you like. Now we want to know that this is not just a pre-bundle, that it's an actual smooth bundle, maybe a vector bundle. So it's a bundle for the category vect M, where M is the dimension of the fiber. And for this, we can induce we can induce local trivializations of this bundle, which are C-infinity compatible, from coordinates of our total space E, as constructed before. So if y1 up to yn, z1 up to zm are the local coordinates on E, induced by coordinates on M and the fiber, and the local trivialization as before, just write as before. Then, how can I come up with a trivialization of this pre-bundle? Then, a trivialization, a local trivialization of the vertical bundle is given by, right, so we have to take an arbitrary vector from this vertical bundle, and we have to associate to this something in the model fiber. The model fiber would be, in this case, Rm, because I'm claiming that this is a vector bundle of rank m, where m is the dimension of the fiber. So to each element here, locally at least, I have to associate a vector in Rm. And how do I do that? Well, I express the vectors in here in the basis, and the basis that I'm using is induced by these coordinates. Now, if you look at the coordinate vector fields of these coordinates on the total space E, which ones span this space? I'm claiming a subset of the corresponding coordinate fields here actually form a basis of this subspace here. Exactly, because these are coordinates on the fiber, and so the corresponding coordinate vector fields span the corresponding tangent space. So any vector here can be written uniquely in the form sum ai dzi I from 1 to n, and I associate to this the vector a1 up to an. So this gives me a local trivialization. It's an isomorphism between this space V of F and Rn. And the thing that one now has to do is to check that if I take two such local trivializations coming from different charts, then the transition between the two is smooth. But this comes from the fact that if you change coordinates on your fiber, then the transition of these coordinate fields is given by smooth functions, namely by the partial derivatives of the coordinates for one system with respect to the other system. So this yields C infinity Good, so that's really a true bundle, and in fact it's a vector bundle because the category that we are talking about in this case is just the category of m-dimensional real vector spaces with isomorphisms between such. Good. So that's the vertical bundle. Now, the interesting thing would be a horizontal bundle, complement for this. There is no canonical horizontal bundle, so we have to turn this basically into a definition. And so the definition is now a horizontal distribution, as it's called. And E is a bundle. And it's in fact also a vector bundle with all the reals, and it's the complementary dimension to the vertical bundle. So the vertical bundle is M, has rank M, so this one has then rank N, like the dimension of the base manifold N. On E. So this maps some point to a certain subspace, again of the tangent space, but this time of dimension n rather than m, and in such a way that the vertical bundle at this point, so that this is a complement for the vertical bundle. So it's in the literature it's called a horizontal distribution. This has nothing to do with distributions in the sense of generalized functions. This is a completely different thing. So this is just a distribution of certain subspaces over the total space of the total space E. So that's a definition. And if we have that, then if we restrict the differential of the projection map, which maps the tangent space of the total space to the tangent space of the base manifold M, if we restrict this to the horizontal subspace, then this maps the horizontal subspace to the corresponding tangent space of M, base manifold I of E. And this is then an isomorphism. Why? Because this linear map, the kernel of this linear map is exactly given by this part. So if I have a complement of the kernel, then the restriction to this complement will certainly be injective. But on the other hand, we also know that the differential is surjective. It's a Piezo submersion. So that's why it's an isomorphism. Well, be careful. I have not yet related this to coordinates in any way, right? I mean, I'm not saying that this subspace of this tangent space is spanned by coordinate fields. Right? So, I mean, previously we had constructed these coordinate systems, and in fact you could take as your h's the span of the coordinates of the y's. You could do that. But in general, these spaces will not be spanned by coordinate fields. At one point, yes, but in general, it's not possible to find coordinates, even locally, that span these h's. It's just some subspaces a priori. But of course, I mean, if we take the span of those, this would be an example. That's true. All right, good. And well, so we have that, and that's a horizontal distribution. And now And the fact that it's a bundle just tells us that it depends smoothly on the point E. Right? That's what it does, basically. It's not just a pre-bundle, but an actual bundle. And once we have that, we can talk about horizontal lifts of vector fields. So, definition, if X is a vector field on the base manifold M, then xh evaluated at a point E, which is defined as, well, take the vector field, which is a vector field on the base manifold, so we can evaluate it at pi of E, which is a point M. And then we can, so that's an element then in here, and we can take the inverse of this isomorphism to get an element in here. So let's do that. So D of D restricted to HE to the -1 applied to this thing. This gives me then an element in HE. So this way, for each E, I get an element in this HE, which in particular is a tangent vector to the total space. And so this whole thing will be a particular kind of vector field on the total space. So then this defines the horizontal lift of X. So given the vector field on the base manifold, we can horizontally lift it to the total space, which is then a vector field on the total space, but a particular kind of vector field, namely one which is lies always in this horizontal space. Okay, good. Now, the next thing we want to observe is we can pull back such horizontal distributions along smooth maps. And this goes as follows. So let F from N to M be a smooth map. In addition to the data we already have, so we have a bundle and we have a horizontal distribution, all on N, and now we want to pull back everything to N. So we know already how to pull back the bundle. Question: can we also pull back the horizontal distribution? In order to write down the formula, the construction in a simple manner, maybe I introduce notation for the projections that come with such splitting. So is the splitting TE as a subspace into a vertical subspace plus horizontal subspace. So this induces two projections. Projection onto the vertical part and the projection onto the horizontal part. So pi E is the projection on the vertical part. And this projection has the horizontal vectors as their kernel. And similarly, the projection onto the horizontal part. With kernel the vertical vectors. That's just notation for these projections. And so we recall that we have this map F tilde used on the total spaces. So from the total space of the Pullback bundle to the the total space of the original bundle. This is over n, this is over m. And now, if we write down pullback of this horizontal distribution, evaluate it at some point E tilde in the total space of the pullback bundle. And I define this as take the differential of the map F tilde, which goes from tangent space vectors here to tangent vectors there, and then project to the vertical part. So then we have, so maybe this is at the point E tilde, so that's a linear map. So this goes from T E tilde of this total space here. Then the map F tilde gives me something that lives in here. So this would be then the tangent space of F tilde, E tilde of the total space of the original bundle. And then I apply this projection map and I land in the vertical subspace of the image point. Right? So this is a map from here to there, and I take the kernel of this. And now I claim that this is a horizontal distribution for the pullback bundle. So what would I have to check? Well, I would have to check that these spaces that I've written down form complements for the vertical bundle of the pullback bundle. Right? That's what I have to check. So let's first check that the sum is direct. So if I look at F star H tilde and intersect with the vertical space at E tilde of the pullback bundle, the claim is that this is trivial. So we need to check two things: that the intersection is zero and that the sum spans everything. And why is that? Well, let's see. If I take something in this intersection, then in particular it's a vertical vector. So it's tangential to a fiber in the pullback bundle. Okay? So let x be this intersection. And I have to show that x must be 0. So since this is a vertical vector, it can be represented by a curve which lies here in the fiber through E tilde. Then there exists a curve C tilde defined on some interval going into a fiber here over the point E tilde, such that C tilde dot of 0 is equal to x. The vector x can be represented by a curve which lies here in this fiber. And that's the same thing as f of f yeah, this is right. Tilde as well. I should say here this is actually pi tilde tilde. Here I have pi f tilde tilde. Okay. So we have that. This is simply because we are in this part. And now let's see what happens if I apply this map to it. So then, IV applied to tilde at E tilde applied to this x is equal to pi b of. So what I have to do, I want to apply the differential of f tilde to this tangent vector. The tangent vector is represented by the curve c tilde. So I can compute this by applying the map f tilde to the curve c tilde and then differentiate. Right? That's essentially the chain rule which defines the differential of f tilde. Okay, but now C tilde was sitting in one fiber. If I apply f tilde to it, I have a curve in this fiber over the original bundle. So this is a curve in the fiber. So this is something which is vertical. So this lies in the vertical space, the original fiber of tilde d tilde. So this is a curve in one fiber of the corresponding. We have something in the pullback bundle lying in the fiber, and the map f tilde maps fiber to fiber. So this is a curve in the fiber, so if I differentiate, I get a vertical vector. And if I project now, this doesn't change anything. So what I get back is the same vector. But now I'm not only, so this has only used that I'm started with a vertical vector, but I also said that it should lie in here. But what is this space? This is the kernel of this map. So I have to get 0. This should give me 0, right? But if this vector is 0, and since this is the identity, this implies that x has to be 0. Right, the map f tilde is the identity between this fiber and that fiber. So the curve differentiated here gets 0, and the curve there gets differentiated 0. And this proves this statement here. And in order to see that this is really a horizontal distribution, the only thing that remains is to check that the dimensions fit. So they intersect trivially. If the dimensions add up to the total dimension of the total space, then this is a complement to that. Okay, so what is the dimension? Let's try to compute the dimension of this thing. So it's a dimension, by definition, the dimension of the kernel of this projection composed with this differential. What's the rank of this linear map? So this maps one fiber identically onto another fiber. So when I differentiate on the corresponding tension spaces, I also get the identity, and then I compose with this projection. And the projection, the rank of this projection, then is just given by the image of the dimension of the image space, and that's the dimension of the base manifold. So the dimension, so the rank of this is dimension of the base manifold, which is n, and the total space on which this is defined is the space, the total space of the pullback bundle. Sorry, this is the projection onto the fiber, so it has the fiber dimension here, right? So it projects on the tension space of the fiber, and the fiber is m-dimensional. Sorry. Okay, but this is good because this tells us exactly that the dimension of this one. I bring the m on the other side. The m is the dimension of the fiber, but that's the same thing as the dimension of the vertical space. It's the same as the dimension of the total space. So this is the correct dimension for the complement. So this shows that f star h at the point e tilde is a direct sum with the vertical space of this pullback bundle. It gives me complete tension space at e tilde of the total space of the pullback bundle. So this way we can pull back horizontal distributions. That's important because it will mean that we can pull back connections, and it will turn out that we can then also pull back curvatures, and this is also will be relevant to our characteristic classes. This can go now. Questions so far? I know it's very formal at the moment, but we just have to go through this now. But that's a geometric construction, which works in complete generality for all seed bundles. So really, when we think of connections, we think of a recipe to differentiate sections in a vector bundle. So how do we get there? And the bridge is given by parallel transport. So let's talk about parallel transport. So when we do parallel transport in a bundle, then we need a curve in the base manifold along which we do the parallel transport. So let C on some interval I in the base manifold be a smooth curve. Let's fix two parameter values, T1 and T2 in I. And now I want to talk about parallel transport in my bundle F over the manifold M along this curve C. So how does this work? And so here we have the base manifold M, curve C, two values, C of T1, C of T2, and over each point of M there is a fiber sitting. In particular here we have the fiber F over C of T1, and here we have the fiber F C of T2. And parallel transport should give me a map from this fiber to that fiber. So taking an element here, parallel transport it along the curve and end up with an element there. So that's what I want to do. I want to construct a map from this fiber to that fiber, somehow using this curve C. Okay, and how do we do that? Well, C is a smooth map from an interval I to my manifold, and here I have these two elements, T1 and T2. And this interval now plays the role of the manifold N that I had previously when I did pullback. Because we can now pull back this bundle along the curve and get a bundle over the interval. I'll pull back. Bundle F. This gives me a pullback bundle C star F over the interval, and also the horizontal distribution that I've chosen in my bundle F. This gives me a pullback horizontal distribution, as I just explained. I can pull back a horizontal distribution as well. And so we have the pullback bundle. So what's the fiber over T1? The fiber over T1 of the pullback bundle is obtained by taking the image point of T1, which is C of T1, and then take the fiber. So the fiber here is f of c of t1, and similarly here I have the fiber f of c of t2. Remember, I want to construct a map from here to there, so I can equally well do this here, because these are the same spaces. So construct a map from here to there. All right, and now I have this. I have taken the horizontal distribution, pulled it back to this bundle over the interval. Now what can I do with this? Well, I can look at horizontal lifts of vector fields. And there is a canonical vector field on the interval, namely the vector field ddt. And I take this canonical vector field ddt and look at its horizontal lift here. So consider, so let y be the horizontal lift of the vector field ddt. So that gives me a horizontal vector field on the total space of this pullback bundle. That's the horizontal vector field on the total space of the pullback bundle. Obtained by, well, horizontally lifting ddt here. So this gives me vectors here, which, when I project them down onto the interval, are just the usual vector field ddt. So if I draw ddt here as this canonical vector field, constant length, I get a vector field on this total space, which projects down to this constant length vector field on the interval. So if I write this somehow in a decomposition of horizontal and vertical, I know that the horizontal part gets to this mapped to this projected to this constant vector field here, and I don't know anything about the vertical part. So this could be anything. But that's my vector field somehow, right? So the projection down is always this constant length vector field ddt. Like this. Anyway, I have some vector field now on my total space of the pullback bundle. And now I can tell you what the map would be from this fiber to that fiber. Whenever I have a point here on this fiber, I just cannot chalk. When I have a point here on the left fiber, I just take this point as my initial value and look at the corresponding integral curve along this vector field. So I look at the integral curve and I follow it until I hit the other fiber. So this gives me a map. Okay. Now consider the map from f of ct1, which is the same thing as the pullback bundle fiber at t1, to f ct2, which is the same thing as the pullback bundle fiber at t2, given by the flow of this vector field. Which is exactly this, right? So you start on your fiber, you follow the integral curve until you hit the other fiber, and then you evaluate. since this integral curve maps to the standard curve here, you know that the integral curve really moves to the right. Now it may happen, so this integral curve can certainly not hit such a fiber twice, because when you project down, it will always move further and further. It cannot come back or anything bad can happen. So this cannot happen. However, what can happen is that the integral curve that starts here doesn't even exist all the way up to the right fiber. So if these vectors go up very steep and fast, then it may happen that this integral curve goes to infinity before hitting this fiber. So possibly this flow of the vector field does not exist long enough for points in this fiber to ever reach that fiber. That might happen. So that's why I write in if defined. And if this happens, if this bad thing happens, then I would say that paratransport is not defined. And so this map is paratransport along the curve C from parameter value T1 to parameter value T2. And this map is called paratransport. It's called parallel transport along C if defined. Of course, later we will look only at situations where it is defined. For instance, if the fiber is compact, then there's no problem. If the fiber F is compact, then the integral curves always exist as long as they exist downstairs. Then there's no problem. But for a vector bundle, for example, fibers are not compact, right? So then one has to do some extra thing. All right, good. This is parallel transport, and this parallel transport has some relatively obvious properties. So let's collect them. First of all, if the map is defined, then it's an isomorphism because you can do the same thing backwards. Right? So if you can do this, so if it's defined, I mean really that it's defined as a diffeomorphism. So that you cannot flow only from left to the right, but also from the right to the left. So that's a diffeomorphism. Okay. And well, properties. First of all, P, T1, T2. So paratransport, or let me write paratransport is invariant under reparameterization of the curve. Let's say orientation preserving or reparameterization. Under what does it mean? Under reparameterization of the curve C. What does this mean? So if I replace the curve C by a curve composed with a reparameterization, so let's say I have T hat is equal to C composed with psi, and psi from interval J to the interval I is a reparameterization, so it's a diffeomorphism of these intervals. And then I could look then the paratransport along the curve C from coincides with the parallel transport along the curve the C hat and C coincide. Of course, we have to fix the corresponding values at which we do that. So if this is for goes from T1 to T2, then this would go from psi of t1 to psi of t2. So that's the same thing. And why is this? Well, if you apply a diffeomorphism to this interval, then the interval gets mapped to another interval by diffeomorphism, and you can just lift this diffeomorphism to map the total spaces, and the corresponding vector fields will be mapped to each other. So you can check this easily. It's no problem. So that's the first invariance property. The next thing would be if you look at the concatenation of two curves. So suppose you have one curve, C, followed by another curve. First, like this. Suppose you have one curve, one big curve, and you subdivide it into two curves. Then you have a curve C1 here, so it goes in this direction, and then another curve C2 here. Then I could do two different things. I could do parallel transport along curve C, or I could do parallel transport along C1, followed by parallel transport along C2. And they are both the same. So, meaning that, so this is C of T1, which is equal to C1 of T1, and then here we have C T2, which is equal to C1 of T2, and also, since parameterization plays no role, I can parameterize C2 also to take the same value, parameter value here. And then here I have C2 of T3, which is the same as C of T3. And so if I take this from T1 to T3, that's the same thing as first parallel translating from T1 to T2 along the curve C1, followed by parallel transport from T2 to T3 along the second curve C2. And that's obvious from the definition, because you just take the flow from one fiber to the second fiber and compose it with the flow from the second fiber to the third fiber. Of course, that's the same thing as taking the flow from the first to the third fiber. That's obvious from the definition. All right. So if we take the same parameter value here, T and T, along any curve, what do we get? Yeah, the identity of the fiber at C of T. Okay. So this second property here can now be used to also define parallel transport, not only when we have smooth curves, but also when we have piecewise smooth curves. So for if C is a piecewise smooth curve, which means that it is a continuous curve, and there is a subdivision of the interval which is defined. It's a subdivision, so let me write this like I would like to work with open intervals, because if I take a closed interval, then this is a manifold with boundary. And I've never talked about manifolds with boundaries, or in particular when I pull back bundles. Right? It's not a problem, I could do that, but it's not necessary to do it either. So I would like to stick with open intervals. So let's say I have, so I is an open interval from A to B, where A can also be minus infinity and B can be plus infinity. So for A minus infinity is less than or equal to A, less than B, and that's less than or equal to plus infinity. And then we have numbers in between, A less than T1, less than T2, less than Tk, less than B. So C is continuous, and we can subdivide our interval in such a way. Such that the restriction to Ti, Ti plus 1 is smooth for each I. So what I just want to say is that I have something like this. I have my curve, which looks like this. It consists of finitely many arcs, which are all smooth and fit together continuously at the breakpoint, at these non-smooth points. So that's my C. And then I put the parallel transport from A to B along this piecewise smooth curve. I just say, okay, I do it for the individual parts. So first from A to T1 along the corresponding restriction composed with T1 to T2. So this is then, now maybe I do compact intervals, not overly complicate the notation. T1, T2, and so on, all the way up to Tk, B, C, composed, restricted to the corresponding interval. So what I'm saying is simply the parallel transport along this curve is defined as first parallel transporting here, then parallel transporting then. And because of this property, this is a reasonable definition, because it doesn't matter whether or not I consider this point as a non-smooth point or not, because this parallel transport is the same as this, followed by that. Okay. Good. Considering piecewise smooth curves is convenient if we want to patch together curves later. Because very often, if we restricted ourselves to smooth curves, then I would have to ensure that they fit together smoothly, which is inconvenient. Yes. From T1 to... Okay, so I should... this is what you mean, right? Yeah. T2, T2, T3, corresponding points here. And finally, Tk minus 1 to Tk, that's true. Yeah, that's true. Good. Good, then my time is up. So next time I will use this parallel transport to define a covariant derivative and to see how we obtain really a connection as we know it from this horizontal distribution via parallel transport construction. The advantage of this approach is that it really works in complete generality, so no matter what bundle we are talking about. That's very good. So in particular, we deal with connections on vector bundles and also with connections on principal bundles at the same time. All right, so thanks. So that's it for today.